So scale factor is the number you multiply lengths by to go from one figure to another. So what we have here, we have rectangle S that is 4 inches for the base and 3 inches for the height. If we were going to apply a scale factor of 2 to this rectangle, what that means is we would double the base. So instead of 4 inches, it would become 4 times 2. It would be 8 inches wide. And we would double the height as well. So instead of being 3 inches high, it would obviously become 6 inches high. So our new rectangle would be a scaled copy of the original that is 8 inches by 6 inches. So you're going to notice some things about these two rectangles. They are what are called scaled copies of one another, which also means they are similar or proportional to one another. Now, if we double the base and we double the height, the perimeter is going to double. So the original perimeter was 4 and 3, which is 7, and another 4 and 3 would be another 7, so that would be 14 inches. And our new perimeter is going to be 8 and 6, which is 14, and then another 14 for the other lengths, and that would be 28 inches. So you notice the perimeter doubled. What does not double would be the angles. Corresponding angles are going to stay the same. This angle in the lower left-hand corner of rectangle S is going to be congruent to the angle in the lower left-hand corner of our new enlarged rectangle. They're both 90 degrees. It did not double. If the angles changed, the shape would change, and they would not be proportional or scaled copies or similar to one another. Now, the area does something a little bit different. So we know the area of rectangle S is going to be 4 times 3. It's going to be 12 inches squared. If we look at the area of our new enlarged rectangle, 8 times 6 is going to be 48 inches squared. So notice that did not double. That's actually 4 times the original area. And the reason it's 4 times the original area is because if it's twice the base and twice the height, we can fit 4 of our original rectangles inside the new one. So if the scale factor was 2, perimeter is twice as big, side lengths are twice as big, but the area is going to be 2 times 2, or that scale factor squared times bigger. So we're going to look at another example here with triangles A and B, and it asks for the scale factor from triangle A to triangle B. Now, one thing we got to know is that if the figure is enlarging, the scale factor is going to be greater than 1. Whereas if the figure is getting smaller, reducing in size, it's going to be less than 1. If we have exact scaled copies of one another, then the scale factor would be just 1. It would stay the exact same. So to find the scale factor between two figures, you want to match up corresponding parts. So I'm going to look at the base of triangle A, which I'm highlighting in blue, and the base of triangle B. Those are corresponding lengths, and it's going from 4 to 6. Now, we're looking for what we're multiplying 4 by to get 6. So, a lot of them you can do in your head, but this one you might not know what you have to multiply 4 by to get 6. So what you can always do is draw your arrow in from the original to the new one, and we're going from A to B. You'll take where the arrow ends, which is going to be at 6, and divide it by where it began, 4, and you're going to get as a decimal 1.5. It's the same as 3 halves. That's what you would get if you simplify it. So that means the base is multiplied by 1.5, which also would mean that the height would have to be multiplied by 1.5. And if we did 3 times 1.5, or 1.5, we would get 4.5. So the answer to the scale factor from A to B is 1.5. Now, if we had asked for the scale factor from B to A, we would be going the opposite direction. It's going to be less than 1 this time because it's getting smaller. So the difference is we would draw the arrow the other direction, and instead of doing 6 divided by 4, we would do 4 divided by 6. And you're going to notice, well, that's just the reciprocal where we flip the numerator and denominator of what it was from A to B. So going the reverse, it's always the reciprocal. Now we could have it as 2/3 as well, or as a decimal. You could say it's times 0.6 repeating or 6/10 repeating. That would be the scale factor going the other direction. Now one more thing to find on this, we have a side that is missing here. We don't know what that longest length on triangle B is, which is actually called the hypotenuse of that right triangle, but we could use our scale factor to find it. So if the hypotenuse, or the longest side opposite of that right angle on triangle A, is 5, if we multiply that by our scale factor by 1.5, we would get that missing dimension, which would be 7.5 meters. Now, we also have the relationships that held true like it did on the previous slide, where if the scale factor is 1.5, all the side lengths are 1.5 the original, the perimeter is going to be 1.5 the original. The angles are not going to be 1.5 times the original. The angles still need to add up to 180 degrees for a triangle, and they would, corresponding angles, be the same as what they were on the original one. So this 90-degree angle here is still a 90-degree angle in triangle B. The area would end up being 1.5 times 1.5, which would end up being 2.25 times the original area. It's that scale factor squared. Let's look at our last example here, and this says, are these two rectangles scaled copies of one another? That means, are they similar, are they proportional to one another? So our original rectangle is 4 centimeters by 7 centimeters, and our new enlarged rectangle is 8 centimeters by 11 centimeters. If we're going to figure out if they are proportional to one another or scaled copies of one another, what we want to do is identify, well, is there a scale factor between them? Is there a number that we're multiplying the side lengths by on one to get the corresponding side lengths on the other that holds true for all of the lengths? Well, I'm going to start with the base of each that I'm highlighting in blue. The base of the original one is 4, the base of our new enlarged one is 8, so we can do 8 divided by 4, and that's going to be twice as much. That means that for them to be proportional to one another, that the height would also need to be twice as much. But if we tried to do 7 and we multiply that by 2, we're going to end up getting 14 centimeters, not 11 centimeters. So we know that these are not proportional to one another because it is not as high as what it needs to be. It's been distorted. So another thing you can do to check whether they are proportional to one another is you can look at ratios inside of the rectangle. What I mean by that is if you look at the relationship between 4 and 7 and how many times bigger 7 is than 4, well, 7 divided by 4, that is going to be 1.75 times as much. So if the height on our original rectangle is 1.75 times the base of our original rectangle, then the height on our new rectangle has to be 1.75 times the base on our new rectangle. And if you do 8 times 1.75, you do not get 11, you actually end up getting 14. So had it been 8 by 14, they would be proportional to one another.